Hello friends, welcome back to our channel. Proceeding further in vectors, we are first of all going to learn representation of different forms of writing a vector quantity. Suppose we are given a vector quantity which is of magnitude 4 units and suppose it is pointing in 30 degree north of east. A vector of magnitude 4 units is pointing 30 degree north of east. This is the form 1 of writing a vector. Now let's see form number 2. We can represent this statement diagrammatically. Let this be north direction, this be east direction, and the vector A vector is of magnitude 4 units and pointing 30 degree north of east. That means from east direction we have to move 30 degree towards north. Let this be the vector A vector whose magnitude is equal to 4 units. That means this length represents 4 units and this angle is 30 degree. This is form number 2, and we can write form number 3 by writing projection, the projection concept. That is, we can write A vector as, suppose this represents the x direction, so let the unit vector in this direction be I cap, and let the unit vector in this direction be j cap. Let us suppose this represents the x direction and this represents the y direction. Then we can write A vector as 4 cos of 30 degree. This length is 4 cos 30 degree and it is I in the direction I cap, plus now we have to see this direction which is 4 sin 30 degree. 4 sin 30 degree j cap. These are the 3 forms of writing a vector. Next, suppose we are given A vector is equal to A1 I cap plus A2 j cap. A vector is equal to A1 I cap plus A2 j cap. Then its magnitude mod of A vector is given as root under A1 square plus A2 square. We have already seen this concept. Next, the angle, let's draw the diagram first. This is suppose A vector, this is suppose x direction, and this is suppose y direction. Then this length is A1 and this length is A2. Let this be theta. The angle made by this A vector with the positive direction of x-axis with plus x-axis is given as theta is equal to tan inverse of A2 upon A1, because tan theta is basically A2 upon A1. So from this statement we can derive this expression. In this way we can find the angle made by the vector A vector with the positive direction of x-axis. Next, we are going to see how can we represent a vector in space. Suppose we take a vector in 3D space. Now any vector, let us suppose a vector can be represented as a vector is equal to a1 I cap plus a2 j cap plus a3 k cap in 3D space, where I cap represents the unit vector along the x-axis, j cap represents the unit vector along the y-axis, and k cap represents the unit vector along the z-axis. Let's see this concept using a simple diagram. Let us draw a cuboid. Suppose this is the x-axis direction, this be the y-axis direction, and this direction be z-axis. This is x, this is y, so this is z-axis. Now let this be a vector. Then its component, its x component, that means its projection in the direction of x-axis is going to be this one, which is a1, and its component in the direction of y-axis is going to be this one, which is a2, and its component in the direction of z-axis is going to be this portion, which is a3. Now this is a1 vector, this is a2 vector, and this is a3 vector. From triangle law of addition, you can see by head-tail combination we have a1 vector plus a2 vector plus a3 vector is going to be the resultant of these three vectors. This is a1 I cap, this is a2 j cap, this is a3 k cap. So we can understand this concept diagrammatically also. Next we are going to see addition subtraction of two vectors written in I cap, j cap, k cap format. Addition, subtraction. Let us suppose we have a vector as a1 I cap plus a2 j cap plus a3 k cap. And similarly, let us suppose we have another vector which is b vector as b1 I cap plus b2 j cap plus b3 k cap. Now first of all we can see the addition. A vector plus b vector equal to a1 I cap plus b1 I cap. So we can take I cap common and we will get a1 plus b1 I cap. It means the x components are added. Similarly, we have a2 plus b2 j cap plus a3 plus b3 j, not j, it will be k cap. Next one is a vector minus b vector. We have a1 minus b1 times I cap plus a2 minus b2 times j cap plus a3 minus b3 times k cap. In this way we can see the addition and subtraction of these two vectors written in I cap, j cap and k cap format. Now we are going to see some properties of this addition and subtraction. The first one is a vector plus b vector is going to be equal to b vector plus a vector. That means we can say that vector addition is commutative. We can write it here as commutative. The second one is a A vector minus B vector is not going to be equal as B vector minus A vector. A vector minus B vector is different from B vector minus A vector. Diagrammatically also it is different, and mathematically obviously it is going to be different. Next we have A vector minus B vector is basically negative of B vector minus A vector. Similar concept we have already seen. Fourth one is A vector plus B vector plus C vector is going to be equal to A vector plus B vector plus C vector, and is also going to be equal to A vector plus C vector plus B vector, or any combination that you can write. It is going to be the associative law. Next one is, suppose K is some scalar quantity. It is any scalar multiplied with A vector plus B vector. Then we can distribute it in two parts, that is K times A vector plus K times B vector. These are some important properties. Next we are going to learn multiplication of vector quantities. Multiplication of vectors. We will find in the chapter vectors there are two types of multiplication. The first one is dot product or scalar product. In case of dot product, the result obtained is a scalar quantity, so that is why it is also named as a scalar product. And the second one is the vector product or cross product. As the name suggests, that in case of cross product we are going to obtain the result as a vector quantity. That is why it is also named as a vector product. Let us start with the dot product. Dot product or scalar product. The dot product between two vectors, that is between suppose A vector and B vector, is denoted as A dot B, and is given as A dot B is equal to magnitude of A vector multiplied with magnitude of B vector multiplied with cos of the angle between the two vectors, that is A vector and B vector. This theta represents the angle between A vector and B vector. This is the definition of dot product. We should also note that one important note, in case of dot product, A dot B is equal to B dot A. And the answer obtained is always scalar. As you can see, this is a number, scalar number. Magnitude of B is also a scalar number, and cos theta is also a scalar number. The product of three scalars is going to be scalar number. Next, let us see some special cases in case of dot product. Special cases. Suppose we have to find the dot product between two vectors which are same. That means a vector dotted with a vector. Then we will get mod of a. By definition, we are getting mod of a and multiplied with mod of a multiplied with cos of the angle between the two vectors. The angle between a vector and a vector is going to be obviously 0. Cos 0, which is 1. So it is going to be mod of a vector whole square. So this is an important formula. A dot a is basically mod of a whole square. This formula is an important one. Now we can see from this concept, suppose we have I cap dot I cap. I cap is also a vector of magnitude 1 but direction along the x-axis. So this is going to be mod of I cap multiplied with cos of the angle between the vectors, which is obviously 0 because it represents the same vector. Cos 0 is going to be 1. Magnitude of I cap is 1 and magnitude of I cap is 1, so it is going to be 1. Therefore, we can note that I cap dot I cap equal to j cap dot j cap is equal to k cap dot k cap is equal to 1. These two are some important expressions. Now, using this formula, we are going to prove that magnitude of a vector plus b vector is going to be root under a square plus b square plus twice ab cos theta, which we have already derived. Now, we are going to prove this formula again using this concept. Suppose we have to prove magnitude of a vector plus b vector is equal to root under a square plus b square plus 2ab cos of the angle between the two vectors, which is theta. Let's start the proof. Suppose we have a vector plus b vector dotted with the same vector, which is a vector plus b vector. Now, we have learned that a vector dot a vector is equal to mod of a vector whole square. So using this formula, we can write it as magnitude of a vector plus b vector whole square. Let me write this portion in left hand side. Is a vector plus b vector mod whole square is equal to, let's open these two brackets, a dot a plus a dot b plus b dot a plus b dot b. Now, a dot a is going to be magnitude of a whole square plus a dot b is going to be magnitude of b multiplied with cos of the angle between them cos theta, and we have already learned that a dot b is similar to b dot a or equal. So we can write 2 times a dot b and we can write it as mod of b cos of theta plus mod b square, or simply we can write it as a square plus this term we can write here as b square plus 2ab cos theta. Now this is mod a plus b whole square, and this is mod of a vector plus b vector this. Here we should write here plus minus sign, but as we know that this is the magnitude of a vector quantity, so it can never be negative. That is why it is always going to be plus sign. So we have proved this formula once again using this concept. Our next special case is, suppose we are given that a dot b is equal to 0. A vector dotted with b vector is producing 0. Then from this equation we can derive that either magnitude of a vector is equal to 0 or magnitude of b vector is equal to 0, or second expression, that is the angle between a vector and b vector is 90 degree. That is, a vector is perpendicular to b vector. Suppose we are given this expression a vector dot b vector equal to 0, then either a mod of a vector equal to 0 or mod of b vector is equal to 0, or the angle between the two vectors is 90 degree. That means a vector is perpendicular to b vector, or we can say a vector and b vector are orthogonal vectors. Only in these two cases the dot product will be 0. And suppose we are given that the dot product of two non-zero vectors is 0, then we are sure that they are orthogonal vectors, because we are saying that these two vectors are non-zero vectors. If these two are stated as non-zero vectors, then they must be perpendicular if their dot product is 0. Using this concept, we can write I cap dot j cap. We have already seen that I cap dot I cap is equal to j cap dot j cap equal to k cap dot k cap is equal to 1. And from the concept that we have already learned, I cap dot j cap is going to be 0, because these two vectors are perpendicular vectors. Similarly, it will be equal to j cap dot k cap, and it will be equal to I cap dot a cap. Any combination will result in the same, that is 0. Next, suppose in the I cap, j cap and k cap format we are given two vectors to be equal. Suppose a vector is equal to b vector, and we are given that a vector, suppose we are given this equation, a vector is equal to b vector, and we know that a vector is equal to a1 I cap plus a2 j cap plus a3 k cap, and it is equal to b1 I cap plus b2 j cap plus b3 k cap. Then from this equation we can write that a1 must be equal to b1. The x components will be same, similarly the y components will be same, similarly the z components will be same. A2 is equal to b2 and a3 is equal to b3. The equality of two vectors means this concept. For example, suppose we are given that 2 I cap plus x j cap is equal to y I cap minus 4 j cap. Then from the equality of the two vectors, the x components must be equal and the y components must be equal. The x component here is 2, so this should be equal to y. That means we have got the value of y, that is y is equal to 2, and the y components, that is here it is x and here it is minus 4. So x will be equal to minus 4. We have got the two values x and y. In this way we can make use of the equality of two vectors concept. Suppose we have the vector a vector is equal to a1 I cap plus a2 j cap plus a3 k cap, and b vector is equal to b1 I cap plus b2 j cap plus b3 k cap. This is b3. Suppose we have to find the dot product of these two vectors a dot b. Then we have a1 I cap plus a2 j cap plus a3 k cap dot b1 I cap plus b2 j cap plus b3 k cap. Next we have to multiply a1 I cap with this whole term. It means a1 b1 I cap dot I cap. We have learned it is 1, so we will get a1 b1. Next one is a1 b2 I cap dot j cap, and it is going to be 0 because these are orthogonal vectors, plus 0 plus a1 b3 I cap dot k cap, and it is also going to be 0. Similarly, we will get a2 b1 j cap dot I cap, which is going to be 0, a2 b2 j cap dot j cap, which is going to be 1. So a2 b2 0 plus a2 b2 plus 0 plus. Similarly, you can proceed further a3 b3. So we have got a1 b1 plus a2 b2 plus a3 b3 a dot b. So here we have learned that if we have to find the dot product of two vectors a vector and b vector given in the I cap j cap format, then we have to simply write the summation of the products of the x components, y components and z components. Suppose we have a vector is equal to a1 I cap a2 j cap plus a3 k cap, and b vector is equal to b1 I cap plus b2 j cap plus b3 k cap. Then we can write a vector dot b vector is equal to a1 b1 plus a2 b2 plus a3 b3. Now here we have this is ab cos theta is equal to a1 b1 plus a2 b2 plus a3 b3. Now here a represents the magnitude of a vector and b represents the magnitude of b vector. So we have theta is equal to cos inverse of a1 b1 plus a2 b2 plus a3 b3 divided by magnitude ab, that is magnitude of a multiplied with magnitude of b. Magnitude of a is basically a1 square plus a2 square plus a3 square multiplied with magnitude of b vector, that is b1 square plus b2 square plus b3 square. Cos of theta will be equal to this term, so therefore theta is equal to cos inverse of this term. Here we have written this: if a vector is equal to a1 I cap plus a2 j cap plus a3 k cap, then from here we can write a magnitude of a vector is equal to root under a1 square plus a2 square plus a3 square. This is a direct formula. We should note that 0 vector is a vector having magnitude 0 and no defined direction. Therefore, we can write 0 vector has no defined direction. has no defined direction. That means its direction is not defined. Now let us draw the 3D plane. Suppose this is x-axis, this is y-axis, and this is z-axis coming perpendicular out of this xy plane. Suppose this vector is a vector, and suppose it makes an angle of alpha with the x-axis and beta with y-axis and gamma with the z-axis. Then we can write a vector dot I cap. That means the dot product of a vector and the unit vector along the x-axis is going to be magnitude of a vector, magnitude of I cap, which is 1, cos of the angle between a vector and I cap, which is alpha. Therefore, from here we can write cos alpha is equal to a vector dot I cap upon magnitude of a vector. Now suppose we write a vector as a1 I cap plus a2 j cap plus a3 k cap. Then we will get here a1, we can write here as a1 I cap plus a2 j cap plus a3 k cap dot I cap by magnitude of a vector. Here the x components will get multiplied, a1 multiplied with the x component here is 1, so it will be a1, a2 multiplied with here y component is 0, so plus 0 plus 0. Therefore we will get a1 upon magnitude of a vector, that is a1 square plus a2 square plus a3 square का square root. This is cos alpha, so alpha is equal to cos inverse of this term. In this way we can write beta as well as gamma. Here cos of beta will be a2 divided by magnitude of a vector, and cos of gamma will be a3 divided by magnitude of a vector. These are some simple derivations. Now next we are going to see projection of a vector on another vector. Suppose we have this as a vector and this vector is b vector. Then if we draw a perpendicular from this point, suppose this is A and this is C and this is B. Let us draw a perpendicular from the point A on the line BC. Then this portion is called the projection of A vector on B vector, which is equal to this, suppose this point is D, which is equal to CD, and CD will be equal to, suppose this angle is theta, then we can write AC cos of theta, AC cos of theta, because AC cos theta is going to be CD. Now here AC is the magnitude of a vector, so in place of AC we can write magnitude of a vector multiplied by cos of theta, cos of theta. Now from the dot product A dot B, A vector dot B vector, we get magnitude of a vector multiplied with magnitude of B vector multiplied with cos of theta. So in place of magnitude of A multiplied with cos theta, we can write A dot B divided by magnitude of B vector. So here we can write A vector dot B vector divided by magnitude of B vector. We have written this using this expression. So we will get A vector dot B cap, because B vector divided by B magnitude of B vector is going to be B cap, and the overall will be positive as a whole, as a result of which we are putting this sign of so that the term is always positive or 0. It should never be negative. In this way, we can write projection of any vector along another vector. We should remember this direct formula. Suppose we know A vector as 7 I cap plus 4 j cap, and we are given B vector as 2 I cap plus 8 j cap. Then if we are to find the projection of A vector on B vector, then we should directly write it as magnitude of A vector dot B cap. That means we have to first of all we have to find the B cap, which is B vector divided by magnitude of V vector, and then after that we have to take dot product of A vector with that of B vector, B cap, and then after that we have to take the magnitude of that quantity.